Record. Okay. Yeah, so welcome back, everyone. I believe this is our last tutorial of this semester, unfortunately. Hopefully, hope you have been doing well. And yeah, so today we're going to talk about parallel programming and why is it useful, especially for M4. Uh, Before we start, just as a reminder, what we are trying to achieve in milestone 4. Basically, it's an open-ended assignment or an open-ended problem where we are given a list of depots, and list of depots were basically depots basically specify where the trucks are initially at, or so you have a courier service, and you want to deliver mails or packages from one intersection to the other. So you are given the list of depots where they start. You are given the pickup intersection. For each order, you have a pickup and a drop-off intersection. Okay, so and some of the pickup intersection can also be a drop-off intersection and vice versa. So it's not necessarily exclusive. Okay, and the goal is to find the fastest delivery route in order to deliver all the packages without uh, we deliver all the packages without leaving any package undelivered in the fastest time possible. And how is this done? Basically, first you need to estimate the travel time between all of the intersections among each other. So from each pickup or drop-off intersection to every other pickup or drop-off intersection. And this will give you an estimate on what is the next intersection I should go to. So if, let's say that right now I dropped off one package. Should I go and I still have packages in the truck? Should I go pick up another package, or should I go drop off one of the packages that I already have before picking up another one again? So that's what the challenge is. We need to figure out what is the best route to minimize the overall time. And you are given 50 seconds to do this. So 50 seconds is a large time, and it's a huge time. You can do a lot of optimization in it. And obviously, there is no one true solution or correct solution to this problem. That's why it's an open-ended, and it's up to you to figure out what to do. So, but to estimate the overall the travel times between every intersection and every other intersection is a good starting point. Where now, okay, now I know that given this matrix that tells me this is the best travel time from intersection K to intersection 1, for example. And this is the best travel time from intersection 1 to intersection K, etc. So given these, we know that they are the best between any two intersections. So this will definitely help us in optimizing the overall route. So not sure if we covered this in the lecture, but there are multiple ways to estimate the travel time. The first one is just estimated by distance. By this, what we mean by this is that given any two intersections, we'll just measure the Euclidean distance between them. This is obviously fast because it's an analytical formulation, and you don't need to do any algorithmic work on it. But it's inaccurate because sometimes, depending on how depending on the edge weights or the street or the speed of the street segment, you can have two intersections that are far from each other, but it's faster to travel between them than two neighboring intersections. Let's say maybe like if you want to travel between two intersections within a city, within 2 blocks, you will use the internal street segments which have speed limit of 40 kilometers per hour, for example. But if there are two far intersections where there is a highway between them, it might be easier to use the highway and faster to reach this one. So obviously, measuring by distance is inaccurate to estimate the travel time. The other option is to actually find the exact path between each intersection and each other intersection using the find shortest path algorithms that you've solved in milestone 3. So this is accurate, but it's much slower because now we need to do an algorithmic work on each pair of intersections. Okay, so the idea is, so in milestone 3, we know that A star is the best, shortest path algorithm between any two given intersections. So given a source and a destination, we can use A star to find the path between them. So the idea to build this matrix will be, we go first over all the intersections, whether they are pickup or drop off, and then another nested loop, which specify the destination right now, also over all the pickup and drop off intersections, and then find a path between them by calling A star. Any idea how fast this is? So if we say that the number of intersections of interest is K, which specify the depot, pickup, drop-off intersections, and N is the total number of intersections in the graph. I'm not going to do the poll, we are two of us, but any idea on what is the time complexity for this?
K squared n log n?
Yes. I'm not sure if this is from the lectures or you actually figured out. If you figured out this, very good.
It was partly given to us in lecture, but it was
okay.
the same.
Yeah, it's easy to figure out. So yeah, K, as Arnaud said, it's K squared n log n. Basically, each call to A star takes n log n, where n is the number of total number of intersections in the graph. And we are doing this K squared times because we have two intersections each of size K. Okay, so some of the large test cases that we have in milestone 4 have like around 500 intersections of interest. So that's like 500 squared times n log n, where n is a large number. So this is a very large number that we might not be able to afford in a reasonable time. So we need to do something better. In order to optimize this, instead of using A star, we can use the simple shortest path algorithm, which is Dijkstra. But instead of stopping at the desired intersection or stopping the algorithm at the desired intersection, we keep traversing and keep doing Dijkstra until we reach all of the desired intersections. This is called multi-destination Dijkstra. So what I mean by this is that, okay, you have multiple intersections. And let me change the color. So, and this is our source. This is my source, and all of these are desired destinations. With one call to the normal Dijkstra's algorithm, we will find the shortest path to this, for example, and then stop. And we usually do this by traversing the graph in waves. Okay, because if you know breadth first search, we start with the neighboring intersections, then we visit the neighboring intersection and start traversing, and then start traversing their neighboring intersections and so on. Okay, so instead of stopping here, we will continue our algorithm until we cover the whole graph. Okay, we are not adding any time complexity other than the n log n that we have. So this is good because now in one shot we will find the path or the shortest path to every other destination from our source. In this case, we don't need to do a loop over K squared. We only need to loop over all the source intersections. So we only need the outer loop. And in the inner loop, we will call path multi-destination Dijkstra. And this is n log n. And this is K. So now we have K n log n, which is much faster than K squared n log n, especially if K is large, which is the case in our test cases. Okay, so this is one way to optimize our code. Okay, so now we brought the time complexity by a huge amount. So what else? Oops, it's not changing the slide. Whoops, just a second, sorry. Yeah. So what if we need more speed? What else can we do? Here comes parallel program, because the kn log n is the best we can do to find the matrix that we've already shown, to find the shortest path between each pair of the intersections of interest. Okay. So what is parallel programming? Nowadays, any CPU that you might encounter has multiple cores on it, and each core it can execute its own instructions, and they all share some shared memory, which is the global memory, basically. And there might also be some internal memory for each core. I'm not going to go over the details of how parallel programming works. If you are interested, you can take the ECE552 in your fourth year computer architecture, or you can go to grad school. It's a parallel programming is a very big research field, and there are always problems to solve. So grad school, you will encounter this if you go into grad school, definitely. So with any application with single thread will not have any problems dealing with the shared memory because the other cores are not doing anything, and you are fully utilizing the shared memory. Okay. The difficulty comes with parallel programming. Now that if we want to run multiple programs or multiple executions of our program on multiple cores at the same time, so now they have a limited resource that they are all sharing, and this is where the major problems in parallel programming come from. Like this, for example. Now they have these two cores have to worry about the shared memory and how to communicate between each other in order to not corrupt the data of the other's application. Okay. So the simplest way of parallelization is what we call it's what we call a basic parallel program, okay, or a parallel program by nature, where each thread can run actually a separate execution of the program without dealing with any shared memory issues because the threads are, or the execution of the threads is independent from each other. What do we mean by this? For example, let's look at this vector addition. We have a vector C which starts the result, and vectors I and B. A and B. Okay. Each instance or each iteration of the loop is actually independent from the other because each iteration is accessing index I of the array or of the vector. So we can give, if we have an infinite amount of threads, we can give each iteration one of these indices. And they are independent of each other because they are not accessing the same element. Okay. So in this course, we use something called OMP, which is a parallel programming library. And the way to parallelize this loop is just by adding this line. We add a pragma OMP parallel for. This tells the program or the compiler that the next for loop that comes immediately will be parallelized. And the way it parallelizes it is based on the number of threads you have. So if you have a 4-core CPU, you either have 4 threads or 8 threads, depending on the architecture of the CPU you have. So let's say that you have only 4 threads. And the way this is parallelized is that the compiler will give quarter of the number of iterations for each one of the threads. So the first thread will go from 0 to 25. The second thread will go from 25 to 50, and so on until we cover the 75 to 100, etc. Now each thread will execute this portion of the code serially. And because this is a parallel by nature program, there will be no problems between any of these thread execution. Okay. Once the loop is done, the code will continue as is, like a normal single-threaded application. Any questions on this? Yes, sounds good. Then let's go do a short demo on using parallelizing a simple program with OpenMP. This is my VNC. Stuff. So we have this simple program, which is like a vector addition. Okay, so we have two vectors, A and B, of length, vector length. And we are just trying to calculate a new we're trying to calculate a new vector that does some operation on both A and B. But you can see here that each iteration relies only on index I, so it's independent from other iterations. So this is parallel by nature program. Okay. And here we are calling pragma openmp parallel for in order to parallelize this thread. And there is a method in openmp to get the number of threads that we have. So let's go compile this and see what we get right now. And remember, whenever we are dealing with speed up or runtime optimization, we always have to compile with the release configuration, which is the most optimized version of the code. Okay, so now let's see what we get. Here it says that the number of threads that we are using is 4, and the elapsed time is around 7.79 times 10 to the negative 5 seconds. Okay, sounds good. Now, this number of threads because we are calling it multiple times in the iteration, might slow us down. So I'm going to comment it for you. Okay, let's see what happens. I don't think it's going to affect the results right now, and I'm getting a warning because right now we are not using the number of threads variable. Okay, it's actually a little bit slower, but this is a compiler optimization. So there isn't much difference in the runtime. Okay, so let's now comment out the parallel instruction. Let's see what we get. So now we are trying to only execute the algorithm on one thread only with a single threaded implementation. Okay, so let's compile again and let's run it. Okay, so notice what happened here. We actually got a runtime of 3.3 times 10 to the negative 5 seconds. With parallelization, we were at 8.9 times 10 to the negative 5 seconds. So our parallel program is actually around 2.5 or 2.6x slower than the single thread. So what are we doing here? Why did we why are we doing parallelization if we're not gaining anything from it? Can anyone think of what is the reason behind this slowdown? So basically, the operating system, I think you're gonna take an operating system next year probably. And the operating system basically has to do some work in order to initialize the threads or in order to run the threads. So this overhead of the work that we have to do is actually more than what we can save with parallel program, with a parallel execution. And the reason behind this is that the vector length is not even that large. So a single threaded is pretty fast. But let's say that we increase this by 3 orders or 4 orders of magnitude. So let's say it's 100, oops, it's 10 million, okay? Now let's see our single threaded execution and how long it will take. Okay. Now here it says it took around 0.03 seconds. So let's now parallelize it and see. Good. Okay. Now we are starting to get 0.02 seconds. But still, this is not a 4x speedup that we are expecting because we have 4 threads. It is only like 30% reduction in the speedup. So let's go increase the number of or the length of the vector by one order of magnitude. So the parallel execution here will take around 0.25 seconds. Okay. The single threaded execution should take 0.38 seconds. So now the speedup is becoming clearer and clearer. I think some students might be using this, so that's not why we're not seeing as much speedup. But usually you will never get up to 4x speedup. 4x speedup is the theoretical upper limit of the speedup that you're gonna get on a four-threaded execution. And usually you don't get to it because there are always overheads in the compiler that the compiler does in order to initialize the threads. So usually you will get up to 3.6 or 3.7x speedup. Any questions on this?
So basically, your input has to be like sufficiently large for parallelization to actually give you any decent results.
Yes. So whenever you want to use parallelization, you have to make sure that it's actually worth it. Because if you have a small problem size, a single execution can be enough. So this comes with trial and error. You always have to try, okay, what is the size, so there's always a trade-off, right? So what is the size that I should be at in order to start seeing speedups in my parallelization? This is basically a summary of what we've seen. So if depending on the vector length, you might or might not get speedups. And as you increase the vector length, the speedup that you gain from the parallelization starts dominating the overhead that you have to pay to initialize the threads. So again, there is a significant overhead to start threads. So you need to do enough work to amortize this overhead over the whole execution time. Okay. So now this was all doing some simple things. Now let's go do more complicated and meaningful things that we can use in our M4. So let's look at the pathfinding algorithm and go back to what we were talking about earlier in trying to do the multi-destination Dijkstra. So just as a reminder, is that okay? Let's say that we have a small test case with k equal 24. That means the intersections of interest are, whether they are depots, pickup, or drop-offs, they are only 24 intersections. Okay. With an iterative A star, in order to calculate the matrix with a single thread, you will get you will implement this in around 32.2 seconds, which is a very long time because that only leaves you around 18 seconds to do the actual optimization on your open-ended problem to find the best traveling courier problem path. With a multi-destination Dijkstra, without any parallelization, but by just algorithmic optimization, we were able to drop this down to 5.86 seconds, which is around 5.5x speedup. Okay. Now let's see what parallelization brings us. So we've parallelized both the iterative A star and the multi-target Dijkstra. Okay. And for the iterative A star, we were able to drop it down to 9.2 seconds, which is around 3.5x speedup. And with the multi-destination Dijkstra, we were able to actually drop it to 1.84 seconds. So compared to the baseline, which is just the iterative A star, this is around a 17.5x speedup, which is a huge speedup and very beneficial, especially now that this leaves us almost all of the 50 seconds requirement to do the actual optimization. So the overall message of this slide is that it's best to first tune the algorithms or try to do algorithmic optimizations before resorting to parallelization. Always make sure that your code is as fast as you can get it on a single threaded implementation before starting to think about, okay, can we parallelize stuff? So let's go do some demos on this multi-destination Dijkstra. We were gonna do a demo on our golden solution. Okay, so I have NetBeans open in here. And just to show you, this is part of our golden solution where we are trying to find the all paths, which is trying to build the vector of vectors of all the paths, okay? And to do this, we are calling it on, we are calling it on all the unique intersections, which are either depots, pickup or drop-off intersections. And for everyone, we are calling the find multiple paths from intersection, which is a function that calls multi-destination Dijkstra. And here we are parallelizing it. Okay, so let's see, let's go and compile this. Let's first clean everything, make sure that we do not have any. Whoops, I need to disable this. The make conf equal release. Uh, almost done.
Just a question out of curiosity, would the compile time also decrease if you parallelize?
Yes, so there is an option to actually, I forgot to add it, and I can show it to you right now.
Okay.
So there is an option to pass it to the make command, which is -j and the number of threads that you have. In this case, we have here 4, so we will say -j4.
Oh, okay. Actually, I remember that you mentioned that in one of the previous tutorials. I
Yeah.
remember now. Okay. Thank you.
Okay. Damn, it's taking a lot of time. I should have actually parallelized this. Could be almost done. Yes, almost. Okay, we're done. So let's go and run the. So just to show you, this is the J. This is how you write it. -j. Whoops. -j4. This is how you write it.
Okay.
But now there is nothing to be done because we've already compiled it. So let's go and run our ECE297 exercise for dash, and we're only running the easy test, which is easy test in Toronto, which has 24 intersections of interest. Okay. So this will tell us how long it took the pathfinding algorithm to finish. Okay, so here it is. It says that the pathfinding took around 1.48 seconds or 1.5 seconds to finish on 24 intersections of interest, which is good. Okay, now let's see the effect of removing the parallel pragma. So now we are running the on a single threaded multi-destination Dijkstra on a single threaded implementation. So first, let's compile it again. Okay. Let's run the ECE297 again. Yeah, it is around 5.5 seconds, which is around 3.6 times slower than the multi-thread implementation. So here it shows that we are actually gaining some meaningful speed up with the multi-threaded implementation. Okay, so this is good. But whenever you deal with parallel programs, you will definitely run into some problems that are harder to debug. Debugging parallel algorithms is more difficult than actually debugging the single-threaded implementation. So here we're going to show you how to debug some of these things. So first, I want to, if you remember that in Dijkstra, multi-destination Dijkstra, we use a priority queue that stores the next intersection with the best time to traverse. Okay. So in here we usually in a parallel program you should define a separate priority queue for each thread that is running. But let's say that we did it as a global data structure. So here we defined a certain uh, priority queue that is global, and this is only defined if we actually define this macro. Okay, so this is just for tutorial purposes, and let's say that we are going to enable it. That means that all of these threads right now uh, will use this priority queue as their data structure. Okay, so they will actually try to read and write from it. And if all of them try to access it at the same time, they might all of the threads try to access the data structure at the same time. They might encounter some problems, and it's hard to debug. So let's see what will happen right now. Okay, I'm going to compile this. And I got some warnings because some other algorithms are still using their own priority queues, but you don't have to worry about it. Okay, so whoops, it looks like dash for some reason. Did I save this? Oh, I didn't save this. So yeah, that's actually a good point. So when I didn't save this, it was still running the single thread implementation, and obviously with the single threaded, the defining it global or internal will not matter because there is only one thread that is using this. So uh, yeah, so actually this is letter. So whenever you want to debug a parallel program, first run it as a single threaded application and make sure that there are no bugs in it. So if it runs properly in a single thread implementation, that means your bug is coming from some race condition. Well, a race condition is like multiple threads trying to access the same resource. If it's not running actually or properly on a single thread implementation, then you have some algorithmic bug. Actually, that is the problem, not the parallel implementation. Okay, yeah. You can notice here that it got stuck. It's not doing anything, or it's meaning that it went into an infinite loop. So there is a problem in here, and I'm going to try and I'm going to stop it now. We also introduced another data structure that is either global or internal, and this data structure basically we store to in it the path nodes. So whenever we find a path to a certain destination, we store the path in this vector. Okay, so let's also uncomment this and see its effect. Again, ignore the wordings. Yeah. Here it says that it crashed. So we have a segmentation fault. Maybe we are trying to, and the reason behind this, and we'll see it in the demo, is that this data structure keeps getting resized. Okay. So maybe we have one thread was accessing an index that has already been out of bound because some other threads already resized this data structure. So we ended up with a segmentation fault that crashed the program. Okay, so how do we debug parallel algorithms? First, you should copy the test files that you have under the public directory under your libstreetmap test folder. I've already copied them here. So I copied the Toronto driver and the easy Toronto.cpp. Okay. Now we are going to run it in under unit test debug. Okay, so let's compile it with unit test debug. And remember, I still have this defined, so it will use all nodes as a global variable. Okay. So let's run it now through the debugger here and see what happens. Okay, it looks like now it is stuck, so I'm going to pause it somewhere to see where I am right now. So I paused it. It is somewhere deep in in the SCL library that we might not know where it is. So let's go to the call stack. And in the call stack, it looks like we are in some destructive function of some data structure, which is the vector in this case. So we keep tracing back until we see something that we are familiar with, which is find multiple paths from intersection. Okay. So it looks like we are stuck at this thing. Okay. I'm going to continue and see if I'm getting stuck at the same point. Again, it's somewhere deep in the code. And let's go back to the call stack and see where find multiple path. Yeah, it looks like all nodes don't clear one. So maybe one thread was trying to actually clear this while another thread has already cleared it because it's a global variable. And to see where each thread is right now, you can go to window and debugging, and you choose the threads window. So this will open a window, a new window, and it will tell you all the threads where they are right now. Okay. So it looks like this. The first thread is at this line. The second thread is at. Oops, it's not double clicking. It's trying to emplace back, which is trying to insert in some in the all node data structure. Okay. And these two threads has already destroyed this function and probably returned from this function. So that's where the error came from. So now we know that, okay, there is a problem in the all nodes data structure. So you go back to where you declared it and see if you can actually do anything about it. In this case, because we made it global, we ran into a problem. So let's go and fix this first. Okay, so whoops. Well, let's close the debugger first. Save it, compile again. Remember, we are running with a unit test debug configuration because we want to debug the unit, what is happening in the unit test. Okay, and now if we run it, it should run fine. It is slower than the 1.5 we're expecting because we are running in a debug mode. So it's not, the compiler didn't optimize our code. So now let's go and uncomment this, the priority queue data structure. So now the priority queue is the global variable. And let's see what happens. Oh, any question before we continue? Okay, good. Let's go debug this. Okay, we started the traveling courier. So right now we are executing probably the find all pass. So let's stop this, see where it is. It is somewhere in the STL library. And let's go look at the call stack. Go back, priority queue. Okay, now go back, find all pass. So it looks like we're stuck because one of the threads is trying to access the top or the front of the priority queue. Okay? While another thread might have already destroyed it. So let's go look at the threads window. So one thread is in find multiple paths. Another thread is in operator equal equal for a priority queue, and the other threads have already probably done. Okay, so this is another race condition, and it's beneficial to look at the threads window to see what each one is doing and try to make sense of why the error occurred. Okay, so let's stop this. So, any questions on the demo? Whoops. So, yeah. So the main takeaway of this is that you have to always be careful when using parallel programs on whether you have a common data structure or not. If you have a common data structure, you need to be very careful on how your threads are communicating with that resource. Because if two threads access it at the same time, the data might be corrupted. So maybe one thread is trying to read the value and the other thread is trying to write to it. And whichever comes first will affect the overall output. It's similar to, imagine you have a bank account, okay, and you are trying to withdraw withdraw money from one ATM machine, and at the same time you told your friend, okay, go uh, deposit this check into my account at this another ATM machine, okay. So uh, depending on whichever comes first, your balance at the end will be different, and especially that if two of them are depositing, then if you might run into race condition because the computer will see, okay, now two of them came at the same time, I'm going to take only one. So yeah, it will only deposit one of the amounts and not the other. So these are called race conditions. In parallel programs, similar to our example, always try to privatize stuff. Privatize stuff. What do we mean by this is that move all of your data structures to within the implementation of the threads. In this case, we want to move the traversal queue to each thread. So declare it inside the while loop or inside the function that the thread is calling. Again, debugging in parallel programs is more difficult than single thread problems. So first, try to disable the parallelism. If the problem disappears, then probably there is a race condition where multiple threads are trying to write and read on a shared variable. Run it through the debugger, use the window threads window to see all threads, examine the call stack to see where you are getting stuck. And if you are accessing a shared variable at a certain crash point, if your program crashes, then this is likely where the race condition is. Okay, there are multiple ways to face race condition. We've seen already one, which is called privatize, which is to privatize variables, make everything local variables. Okay, there is another way called by adding a keyword to the OMP command called critical. OMP critical basically tells the threads that you will share this resource, but whenever you want to use it, only one of you can use it at a time. Okay, so this will force the threads to communicate between each other in order to see when the resource is available. You will cover this in the lecture, I think, this week. And the problem with this OMP critical is that it makes your solution, it makes your performance slower. Sorry. Because now all of the threads are waiting until one of the threads is finishing using the resource. So there is a lot of idle time where you're not doing anything. Okay. The next thing we want to talk about is Amdahl's law. Amdahl's law is a law that tells you how fast, what is the theoretical limit of the speed up that you can get. And this, so which means that let's say that you have an infinite amount of processors where you can use to parallelize stuff. At some point, your speed up will saturate. And this is controlled by the serial portion of your code. So if there is a portion of your code that cannot be parallelized whatsoever, it will always be dominated by this. Let's say that your, sorry, let me grab annotator here. So let's say that you have 50% of your code that can be parallel. So no matter how many processors you have, the best you can get is a 2x speedup. If you have 95% of your code that can be parallelized, and only 5% that is serial, then the best you can do is around 20x speedup. So this tells you that before actually going into parallelizing things with parallel programming, make sure that you have actually make sure that it is worth it. Make sure that you have a good portion of your code that can be parallelized, so that you can you spend so that it's worth spending the time on to optimize. Okay, and so yeah, just a takeaway. Before going into parallel programs, you improve your algorithm first. Usually, this results in bigger rewards. We've seen that going from multi-destination Dijkstra, going from A star to multi-destination Dijkstra gave us around 5 to 6x speedup. Okay, once you are confident that your serial implementation is fully optimized, then use the OpenMP pragmas and start parallelizing your work. Avoid modifying shared state or shared variables. So always try to privatize variables so each thread has its own copy. Okay. And if you want to have a meaningful gain of your speedup, then try to parallelize large chunks of your work. Remember that when we are trying to parallelize the vector addition, at small sizes of the vector, we actually saw a slowdown with OpenMP threads. Okay. And again, parallelogramming is really hard. Even experts can get it wrong. I still struggle when I want to parallelize things. I always run into problems. So, and parallelizing in general is an open research question, and there are always more ways to make it better or easier. So if you encounter problems, you're not the only person that does it. Okay. So just as before we finish, just these are some info suggestions. Before trying to optimize anything, get a very simple approach working first. Even if it has a very bad quality of results and you're not doing well on the leaderboard, that means at least you have a solution that you can submit. Once you have this, then try to use better cost estimates and try to do some algorithmic optimization before any parallelization. Okay. Once you are confident that, okay, this is very good, then start parallelizing in order to minimize your runtime so that you can attempt more number of optimization iterations. Because you have 50 seconds, which is a huge amount of time if your code is pretty fast. And that's it for today. If you have any questions, feel free to ask. If not, then it was nice meeting all of you, and best of luck on the rest of the semester, because this is our last tutorial. So.
Yeah, I just have a question regarding what we talked about in the very, very beginning, regarding the matrix.
Yeah.
Just once again, like when we have the matrix, our next step is to like extract a path. So or make a path from the timings. So you said to use greedy, but that doesn't give you an optimal solution. Like maybe not good enough to be TA good.
Yes. First, it really depends on which intersection you're going to start at, right?
Yeah.
So maybe like let's say that you start at intersection one, like you picked up randomly intersection one to start at, right? Then whatever you choose next is controlled by your first decision, right? Because now your overall path will always start at this intersection. However, if you start at another intersection, uh, you might have a better or a worse solution. You don't know, right?
Mhm.
So with greedy, you are always choosing the next best intersection. So whatever your first intersection is, you're always controlled. Your next best is always controlled by this one, right? So
Mhm.
so that's where greedy might not give you the best result, but it might put you above TA moderate on the leaderboard.
Right. And we can make this even more optimal by using two opt, right?
Two up, and you can also use three up,
And
like
this
which is a more
okay.
complex algorithm. So you can read about it online.
Right. And these both of these are built on top of the greedy?
No, not necessarily. These are total. So, like in optimization algorithms, especially in the CAT field and problems like this, there are a lot of heuristics out there. So you have to read a lot about them. One algorithm is called, I'm not sure if you covered it already in the lectures or not. It's called simulated annealing. I'm not sure if you
Yeah, we
covered it.
briefly covered it.
Yeah, simulated annealing is like a very well-known optimization algorithm that can help you get out of local minima, because when it comes to optimization problems that are highly nonlinear and controlled by many factors, you can easily get stuck in local minima where like you think that you are at the best you can do, but your global optimum or your best solution might be far away from where you are. So these are all open-ended problems, and there is no one correct solution. But and they are not based on each other. So the solutions might be totally different. Simulated annealing is totally different from two opt, for example.
Okay. Okay. So I guess in a way, like, would there be even a point to implement greedy if like we know that let's say we can implement two opt and that'll give us a better optimal
No,
solution anyways.
no, you should definitely implement greedy first. Again, have something working first before going into complicated things. Because if
Okay.
you might end up at the deadline having nothing working, so which is not
Right.
desired, right? So
Right. Okay. I understand. Actually, I had one more question. Regarding the parallelization. So you were, I think, commenting out like the bad parallel